Okay, so this next video for Math 1560 Calculus 1 at U of L for fall 2017 will introduce the definite integral. So we've got most of the preparation out of the way now. We've introduced the idea of using rectangles to approximate area under a curve. We've looked at partitions. We've done pretty much everything except for write down the definition. And so what we've seen so far is that if we want to calculate area under a curve, then we approximate using these rectangles. And what we've seen is that the more rectangles we use, the better our approximation is going to be. So there are two ways of thinking about the definition of the integral. The first is to sort of think of it as something that you define in terms of area. So if I had, for example, some graph, and maybe it looks something like this, right? Here's my graph. Y equals f of x, and let's say I'm going from x equals a over to x equals b, and maybe b is, let's go right to the end, so b is here. Okay, and you want to think of the integral as giving you the area under a curve. Well, that works perfectly well if you're dealing with a function that is strictly positive, or at least never negative. But most functions are going to be some, in some places they'll be above the x-axis, some places they'll be below, right? They can be both positive and negative. So what you do is you come up with this idea of sort of signed area, total signed area. So you have kind of this area 1 here, okay, which is the area which is bounded by the graph and the x-axis, from A up to whatever this point of intercept is here, and then you have this area 2, which is the area bounded by the x-axis and our graph, from that intercept up to this other x-intercept, and then there's this little tiny area in here, right, area 3, because there's this little bit of the graph that comes back above the axis. And what we do is if we basically assign a negative value to area that's below the, well, let's specify below the x-axis. Okay, and so if we take this approach that areas below the x-axis are assigned negative values, then we can say, okay, well, the integral is sort of this total area, so the integral from a to b fx dx, we'd say, well, that's area 1 minus area 2, because area 2 lies below the x-axis, plus area 3. So this is one way that you can think about the integral. You can think of it this sort of total signed area. But of course, that doesn't really help us with calculations, right? Or even with approximations. We want some way of actually kind of getting some numbers out. If we know the function, how do we calculate this a1, a2, a3? How do we get some idea? Well, we know that we can approximate those areas using Riemann's sums, right? We can use these approximating rectangles. So how did that work? Well, we have our graph. So what did our graph look like? Something like that, right? And we want to approximate the area. And so if we were doing, say, this first area here, area 1, what we do is we take this region, we divide it up into pieces. This is our partition. And then we put in these rectangles, right? So we build these rectangles where the height of the rectangle is dictated by the y values on the graph. You choose some point on the graph on each of those intervals. You construct a rectangle of the appropriate height. And then when you come to the area lying below the axis, well, you draw rectangles, but you just draw them, and now the y values are kind of below the x-axis, right? So you go something like this. And again, for each of these rectangles, you're choosing some point on the graph, right? So this is going to be some point xi, well, maybe not xi, because it might be between one of the points, but it's going to be this point. What was the notation we used? C. ci f of ci, right, where this ci is between xi minus 1 and xi at some point in interval I, whatever I is. I guess for the way we draw it, I would be what, 1, 2, 3, 4, 5, 6, 7, 8. So that's C8, let's say, right? And now, of course, f of ci is negative there, and so this kind of corresponds to what we were doing before, although only approximately, in that well, this part here is always bigger than 0, right? These delta x's are always positive. The f of ci could be either positive or negative depending on where the graph is, and so whenever the graph is below the x-axis, this product f of ci times delta xi, giving us the area of the rectangle, comes out to be negative, so we do get this signed area. So now, to turn this into a definition, to define the integral, what we do, and now there's a fair amount of analysis that goes into this. You have to kind of look at things carefully, and you have to, you want to understand whether or not things are actually going to work out for you. But what you can find is that for sufficiently well-behaved functions, and in particular for any continuous function, the more rectangles you use, the better this approximation gets. And one of the ways that you can measure the quality of your approximation is if you use these upper and lower sums that we talked about. You find that every time you add another rectangle, the upper sum gets a little smaller and the lower sum gets a little bit bigger, and as you keep adding more and more rectangles, they meet somewhere in between. And so the true value, the kind of when the approximation becomes exact, is going to be, well, when you take sort of this arbitrarily large number of rectangles. So what you want to do here is, in some sense, consider a limit. You want to consider the limit as the number of rectangles becomes larger and larger and larger, so you want the limit as n goes to infinity. And so we see that here, right? So what you do is you take a uniform partition. So we're going to define this in terms of uniform partitions. This is certainly not the most general definition you can give for the definite integral, but for the purposes of Math 1560, it does the job. Okay, we're not looking at any kind of bizarre, exotic situations where this definition might not be perfectly adequate. So for a given n and a given interval and a given function, we construct this Riemann sum using n rectangles, uniform partition with n rectangles. Okay, we calculate the value of the Riemann sum, and if we can calculate that value and if we can express it in terms of n, in terms of the number of rectangles, then we consider this, then we're able to consider the limit. We look at the limit as n goes to infinity, and we hope that this comes out to a number. So if this limit exists, if it actually comes out and it gives us a number, then this is our definite integral. So in most cases, we're going to find that for the vast majority of functions, when you try to write this thing down, you get something that it's kind of hopeless. We have no idea how we would actually evaluate this limit. And we're going to see that, well, there are ways of doing it, but you can't do it directly. You have to do it via the fundamental theorem of calculus. And in some ways, the fundamental theorem of calculus, it really is an important result. In some ways, it's almost a miracle that things work out the way they do, and we're going to see that as we go forward. So we'll do a few basic examples to show you how you might try and calculate these things straight from the definition, if for no other reason than to convince ourselves that we never want to do that again, and then we're going to move on to the fundamental theorem of calculus.